A lot of the concepts that we're going to be doing in these additional notes are the same or similar to what we've already done in our first note. So some of it's going to be review, but there are some parts to permutations that wasn't covered in your textbooks that we're going to look at. And then I have a number of questions that we're going to do as well. Now, permutations and this whole unit is part of a branch of mathematics called combinatorics, and that's all about counting things. So the first thing which we've already done is the fundamental counting principle. Here's an example. A new car is being built. You have these choices. So the fundamental counting principle is based around spaces. And with our spaces, we make a space for every decision we need to make. So in this example, how many decisions need to be made? 3 decisions. What are those decisions? Your color, your transmission, and your interior. And then how many choices do you have for each of those decisions? 3 choices for color, 2 for transmissions, and 2 for your interior. So you get 12 in total. And so the spaces allow us to count that very quickly. Now, one of the things the textbook didn't do as much of was this idea of sometimes in permutations we're not allowed to repeat things, like in our passwords using names. You could only use a letter once, then it was gone. And sometimes you're allowed to repeat things. So some examples, if you're rearranging the letters of a word for a scramble, and someone has to unscramble that word, well, then you're not allowed to repeat the letters because you'll change the word. But if you're making something like a telephone number, well, you're allowed to repeat numbers because you can have the same number more than once. So sometimes we count things where things are allowed to be repeated, and sometimes they're not. So if we have a 3-digit number, we have to make 3 decisions for those 3 digits, and you're allowed to repeat using the numbers 1 through 7. Well, then there's 7 choices here, 7 choices here, 7 choices here. For 343 total. With repetition, no, that's without, oops. That was bad. There we go. Wait for it. And move it over there. Take those little lines. There we go. That's with repetition. Without repetition, still be 3 decisions. How many choices for the first one? 7, then 6, then 5. So if you weren't allowed to repeat, you'd only have 210 options. If you were allowed to repeat, there would be more options. Now, I would still like to use the numbers 1 to 7 in example 3 and example 4. But this is our first one with a restriction. And I'm not sure that any of your questions up till now in your homework have dealt with restrictions. So we have the spaces strategy, but within the spaces strategy, there's going to be things with restrictions. And the strategy that you're going to find out that you're going to use for restriction problems is deal with that restriction first. So what does that mean? How many 3-digit numbers using 1 to 7, no repetition, are even? So what we have is we still have 3 decisions, but there's a restriction on this last one that it has to be even. Now, if you were thinking about this without knowing that you had to deal with the restriction first, if you looked at your first space, you'd say, how many choices do I have? I have 7 choices. And then my second space, I've used up 1. I now have 6 left. But then when I get to my third space, what number do I put into that even one? Well, how many even numbers are there? There's 3. So you might say, let's put a 3 there. But what happens if you picked one of your even numbers already with the 7? Then there wouldn't be 3 left. So then maybe you should put a 2 here. But what happens if you picked an even one for your 7 and an even one for your 6? Then you would only have 1 left. So how do we do this? 7 times 6 times 3 or 2 or 1? That would be hard to put into your calculator. So what we do is we say, well, let's start here. Even though it's my last number, my restriction is on this even one. I'm going to pick one of those 3 even numbers and put it there first. So 2, 4, or 6, those are our even numbers. You put one of them there. You don't know which one, but you do that first. Now how many choices do you have here? Now you have 6 here, and now you have 5 here. And there will be 90 total ways to count it for an even number. So even though it's the last number, you choose that first. And I'll give you 90 total ways to guess it. So I want you to try and think about this one. Again, we'll use the numbers 1 through 7 in example 4. How many are odd? And once you get your answer, see if you can see another strategy to get that same answer. Because I'm thinking most of you did this, right? 3 spaces. There's a restriction, so you put odd here. How many choices of odd numbers are there from 1 to 7? 4. And now you've used up one of the numbers, right? There's 4 odd numbers. One of them is used up. 6 choices left here. Another number is used up. 5 choices are left. So you get 120. Did anyone see another way that you could get 120? I'll give you a hint. You have to use answers that you already got in previous questions. So why minus 90? That's how many are even. And earlier, we figured out that 210 was all of them, right? 7, 6, 5. So if we did all of them minus the even, we get 120. Does that make sense as another way of figuring it out? Because if we subtract the even ones, all that is left is the odd ones. Now, I'm going to call this another strategy because we're going to use it later quite a bit. It's called the not strategy is what I call it. Because you count what you're not supposed to, right? We weren't supposed to count the even ones. This question says count the odd ones. Well, we counted the even ones. That's not what you're not supposed to count. You're supposed to count the odd ones, but you count the opposite. And so the not strategy, I basically call count all of them, subtract the bad ones, and if you subtract the bad ones, you're going to be left with what you wanted to count to begin with. So already we've been introduced to some new strategies today. With this, we've been introduced to the spaces with restrictions, where you have to deal with your restriction first. And now within it, we see another strategy we could use for counting, where we could count all of them, subtract the bad ones, and we'd be left with what we want to count. And I'm going to call that our not strategy. How many 3-digit numbers can be created using 0 to 9 without repetition? Three decisions, because you're making a 3-digit number. Any restrictions? Tell me, is the following a 3-digit number? No. Is it a 3-digit number if I put a 0 in front of it? Or is it still 32? So there is a restriction that our first digit can't be a 0. Because otherwise, if you put a 0 first, really, that's a 2-digit number. So there's a difference between a number and a code. If you had a 3-digit code to get into your house, it could start with a 0. 032 could be the code. But if you're talking about a number, 32 is a 2-digit number. Doesn't matter if you put 18 zeros in front of it, it's still 32. So if this is not a 0, how many choices do I have for that first digit? 9. Then how many choices do I have for my second digit if you're not allowed to repeat? 9, because now you've used up one number, but 0 gets thrown back in. So we still have 9. And then 8 for 648 total values. Again, we've also already learned factorial notation. Mental math, you always expand the bigger one. So this one is probably easy to see is 42. That came up in a question before. In the second one, if you were doing mental math, this is how I'd show my work. I'm going to start expanding the bigger one, and the 10 is obviously the biggest, until I get to one of the ones on the bottom, which is 6 factorial, because there's a 6 factorial on the bottom. So I know that those are going to cancel out. My 4 factorial, if I expand that, would be 4 times 3 times 2 times 1. Can you see that 4 times 2 is 8? So I can simplify my 4 and my 2 with my 8. And can you see that 9 divided by 3 can simplify to 3 over 1? And once you've done that, everything on the bottom has simplified. And on the left, what are the numbers that are left? You're left with a 10, a 3, and a 7. Mental math, 21 times 10, 210. And then where things get a little bit more difficult is when you start working with factorial notation and variables. So when we're trying to simplify n plus 2 over n factorial, we use the same strategy that we do with numbers, that is expanding the bigger one until you get to the smaller one, like I did with the 10 until I got down to the 6, except now you have to figure out which is bigger. Is n plus 2 bigger, or is n bigger? N plus 2 is the bigger one, so we start expanding that bigger one until we get to the one that's on the bottom. You can write a factorial after that one because it would keep on going, but that will cancel out with the n factorial on the bottom. And then you'd be left with just n plus 2 times n plus 1. Now, permutation, as another, we've already seen, that's when you have a bunch of objects and you want to arrange them. The key thing to a permutation is that the order is important. And the reason we say that now is because later we're going to do combinations, and combinations are where the order isn't important. So there's some things where you have to get the right order. If you're in a race, first is better than second, is better than third. And there are some things where the order doesn't matter. Some card games, you get 5 cards. It doesn't matter the order they dealt them to you. You can rearrange them. But it's still, so those ones, the order doesn't matter. Same thing with lottery, right? If you have to pick the numbers, if you pick all the right numbers, and then you go and say, I won, they say, no, you picked them in the wrong order, you'd be pretty mad. So the order doesn't matter when you play certain lottery games either. But for permutations, order does matter. So A, B, and C, if you wanted to write them all out, and I'm going to try to do it systematically. I'm going to do all the ones starting with A, then all the ones starting with B, And finally, all the ones starting with C. And we get 6 in total. Of course, we know that the answer to this from our previous experience is just 3 factorial, because if you're rearranging it, you'd have 3 spaces. And as you use up a choice, the numbers go down by 1. We've already seen the formula, and we know that this formula is on our formula sheet, NPR. And this is for taking, say you have 10 people in the race and you want to figure out how many ways they can finish first, second, and third. Well, as a permutation, you have 3 spaces, and this is the total number of choices that you start with, which is 10. So probably you would solve that with spaces 10 times 9 times 8, but you could also show it with the formula. Remember when we had 0 factorial as a definition being 1? Well, if you have n objects in n spaces, or npn, that's like all the arrangements possible, that's going to be n factorial. However, if you're looking at this and you're simplifying it, putting it in the formula gives you a 0 factorial on the bottom. That 0 factorial on the bottom has to be a 1 in order for this formula to work. So find the number of ways a program where the order matters of 4 pieces of music can be made from the wind ensemble's repertoire of 10 pieces. Well, you'd have 4 decisions to make, so you could do it as 10 times 9 times 8 times 7. But this is the same as 10p4. Find the number of permutations of the word math. Well, simplistically, this is just 4 factorial. We don't have identical objects here, so it's just 4 factorial. This question in particular is harder than it needs to be. 5 people come in for math help, and there's 12 desks. How many ways can the students be seated if the order matters? You know, sitting at the front, you might get more help than if you sit in the back corner. So what's hard about this question is that when students want to make spaces for this one, for their decisions, they want to make 12 spaces because you get used to putting, you're used to putting students into desks, not desks into students. But you have to remember that with your spaces question, each space represents not a desk, but a space represents a decision. So if there's 5 students that need to pick a spot, they each have to make a decision. So in this example, there wouldn't be 12 spaces, but 5 spaces, because that represents how many decisions need to be made. Student 1 comes in, how many choices do they have? 12, okay? Student 2 comes in, right? I don't know if you've ever come in for math help. It gets very awkward if the second person comes in and sits on the lap of the first person. So usually they don't choose the same desk. So then we have 11, then 10, then 9, then 8. And this is the same as 12p5. 5 spaces starting with the number 12. How many different seating plans could we have in this classroom? So if I hit the random button and I said, if you guess the seating plan correctly, you get 100% in the course, you don't have to come back for the rest of the year. How safe would that be? And just to mix it up, you could sit anywhere in the class. So right now we have what, 5, 10, 15, 20, 25, 28 desks. And there are 17 of you. So with 28 desks, 17 of you, there'd be 17 decisions. And instead of drawing out the spaces, with something big, this is where the notation is nice. You'd have 17 spaces starting with the number 28. If you do that on your calculator, oh, can you find the P button on your calculator? So when using this button on your calculator, because again, that could save you time instead of having to do 28 times 17, 27 times 26. In order to do it on your calculator, you type in 28 first, hit your math button, go over to probability. The second one is NPR. Maybe you have a new version where it comes up and puts that 28 small. If you have, oops, 17. If you have an older version, it just, you do 28, then NPR shows up, and then you would write 17 after. What are your chances of guessing this right? 7.63 times 10 to the 21. That, I find scientific notation doesn't always 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Oh yeah, there's roughly your chances 1 in that amount. We're going to change this so it matches the language that we used before. So we're going to get rid of repetitions here. And we're going to write in identical objects. So permutations with identical objects. Very nice. How many permutations would there be with the word egg? Well, we've done this before. Normally it would have been 3 factorial, but we've got 2 g's, so we got to divide by 2 factorial. Assisipi, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 factorial normally, but we have 3 s's, 2 p's, 2 i's. So we did this earlier today, permutations with identical objects. Now we're going to be doing some more of those. Contractor sold model homes of type A, B, and C on a street. She sold 3 of model A, 4 of model B, and 2 of model C. So when we read this question, we recognize that there are some identical objects. And when you recognize that there are identical objects, you try to think of a way with letters that you could represent this so it becomes like a word like Mississippi. So in this one, 3 of model A, 4 of model B, and 2 of model C. Normally that would be 9 factorial, but we have to divide out our identical objects. Now when you're typing this into your calculator, use your fraction button. If you don't have that fraction button, you'd have to put the bottom into brackets. You know where to find the factorial button, but you're going to find out that sometimes it takes a long time to always get to that factorial button. So it is worthwhile having some factorials memorized or mental math. 2 factorial. Oh, shoot, that's 2 times 1. What? Instead of having to write 2 factorial, you should know that that's 2. Right? 3 factorial. 3 times 2 times 1. That's 6. That's not that hard. 4 factorial. 4 times 3 times 2 times 1. 24. So I would suggest when you can, simplify it in your head. Obviously 9 factorial, that's a very big number. So that one's one that you probably wouldn't do. You'd use your calculator for. This is another one with blocks north and blocks east. We won't draw the grid. We did that earlier. 1, 2, 3, 4, 5, 6. So this would be 9 factorial over 6 factorial, 3 factorial. And now here's another new strategy. So we haven't done any permutations with restriction, and that restriction is things need to be grouped together. This is what we will call this strategy. We will talk about this strategy as the grouping strategy. I think in section C of the homework, there was a grouping strategy question. What it says is, let's say I decide to organize something. I want to organize my books on my shelf. And I've got calculus books. I think I even got that example coming up. We'll do this example first, then I've got calculus books, I've got algebra books, and I've got geometry books. And I want to rearrange them and figure out ways, but I want to keep the different subject areas together. So this is a grouping question because within your arrangements, certain things need to be grouped together. And the way that it's done is you always figure out your groups first. So we make one space, one decision. One decision is how many groups do we have? And in this case, we have 3 groups because I have a calculus books, algebra books, and geometry books. Those are my 3 groups. How many ways could I arrange those 3 groups? That would be, my number of choices would be 3 factorial because it would be calculus, algebra, geometry, or calculus, geometry, algebra, blah, 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 and so on and so on. Okay? Then after you've decided on your groups, you need to make your arrangements within your groups. So it doesn't matter what order you put them down, but I could have had calculus, then algebra, then geometry as my choice here. How many ways can I arrange my calculus books? Well, I have 4 calculus books. They could be arranged in 4 factorial ways. Then my next decision, my algebra books. How many choices would I have for rearranging my algebra books? 5 factorial. And finally, my geometry books, 4 factorial. Since these are each decisions in spaces, you would multiply those all together and get your entire subject. So on the slide before, that's what the grouping session says. We say how many groups factorial, then group A factorial, group B, numbering group B factorial, and so on and so on and so on. Sometimes you will get groups of 1, and we're going to get an example of that today. What does it look like if something is in a group of 1? It's still part of the overall groups, but 1 factorial afterwards won't be necessary. All right. I think I mentioned it earlier. We might get a question with Bill. Here it is. So 5 people, Amy, Bill, Jill, Lee, and Tom, are all, every week they go to this park bench and they sit down. But in this particular week, something's different, and Jill and Bill wish to sit together. It's a perfect springtime question. Okay, so how many ways can this be done? Well, if you think of the 5 people, but 2 have to be together, that makes it a grouping question. So if those 2 are together and the other 3 doesn't matter if they're together or not, can you see that that makes 4 groups? 1 group of 2 and 3 individuals. So when we're figuring this out, there's 4 groups, so that would be 4 factorial. Another way that sometimes people see this is they think about gluing Jill and Bill together and they now become a new person, a single person that's inseparable. Maybe you've seen that with with certain couples. They're never apart. They're like glued together. And so we have 4 people now. We've got Amy, Lee, Tom, and Jabil, which is now 1 person because they're never apart. So that might be the case. So we have number of groups, 4 factorial. Then in each of those groups, the one group is the Jill-Bill group. There's 2 people in that group, so they could be glued together with left shoulder or right shoulder. They could be glued together right shoulder and left shoulder. There's 2 ways that they could be arranged on that bench but still be sitting together. Then each of the other ones, and you wouldn't have to Tom, Lee, and Amy. You could write 1 factorial if you wanted, but this whole section, you wouldn't have to write it if you didn't want to. But sometimes in a grouping question, if you like to say how many groups I have and then draw a space for each of your groups, sometimes it's nice to write it down. So this just becomes 4 factorial 24 times 2, 48 ways that they could come and sit on the bench and Jill and Bill need to be together. Part B. Poor Tom. So next week, don't worry, Tom gets his revenge in part C. Next week, they come to the park bench. Jill and Bill still want to sit together. And now Lee and Amy also want to sit together. So now we're gluing Jill and Bill together, and the Lamey, and then Tom's left. So how many groups do we have? Oops, groups. We now have 3 groups, and we can draw it out like this. This is a group, and poor Tom is in a group all by himself. So there's 3 groups, so the number of ways we can arrange those groups would be 3 factorial. So you could draw your 3 spaces. This could be the Jill-Bill group, the Lee-Amy group, and the Tom group. And this would be 2 factorial, 2 factorial, still 1 factorial. All right. Part C, the revenge of Tom. Something happens during the week, and now Jill and Bill must not sit together. So I don't know what happened, but they will not sit beside each other on the park bench the next week. Usually when something this catastrophic happens, those 5 friends probably have an awkward week where nobody goes to the park bench, but no, they still go to the park bench and still decide to sit down, but now Jill and Bill will not be sitting next to each other. According to what we have as parameters here, we're not sure about Lee and Amy. They're sort of on again, off again, so they could sit together. They don't have to. That's fine. But we want to make sure that Jill and Bill do not sit together. So in order to figure that out, and I've already got it in your notes here, is we do what we mentioned before, something called the not strategy. It would be hard to count directly the number of ways that Jill and Bill don't sit together. Because if you start with spaces, so I start with 5 spaces. Okay, well I have 5 choices here, because anybody could sit there, but then I don't know what to put here. Because if this was either Jill or Bill, then I don't have as many choices next. So it gets really hard to figure out what numbers I should put in because I don't know where people are sitting. It is easier to count using the not strategy. And what the not strategy says is, first find out how many there are in total. 5 people on a bench, 5 factorial, no problem. Once you have all of them, then you count the bad ones. We counted the bad ones in part A. That was where Jill and Bill did sit together. And we had 48 total ways for that. Then if you've counted all the ways and then have the bad ways, if you subtract them, what you're going to be left with is all the rest. And all the rest have to be the ones where Jill and Bill are not together. And so this is the not strategy, where sometimes it's easier to count the bad ways and subtract it from all the ways than it is to count something directly. And I call it the not strategy because it often comes up in questions like this one, where Jill and Bill must not sit together. So then you think of the opposite, and that might be easier to count. Okay, we're going to leave permutations with cases until Tuesday.